This is the ROS Developers Podcast, episode 54.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS Developers, and welcome to the ROS Developers Podcast, the podcast that gives you insights from the experts about how to program your robots with ROS. This is Ricardo Tellez from The Construct, and today I would like to dedicate the podcast to all those ROS developers that are creating a robotics startup. But I mean, based on real robots. Real hardware. And also you make your robots based in ROS. So that's amazing. You are the best, and you are very brave. And because of that, this episode is dedicated to you. Today it is my pleasure to introduce you two people here at the podcast, Gregory Epps and Charles from React Robotics. Greg is the CEO of React Robotics, and Charles is the CTO of React Robotics. And what is React Robotics? It's a company based in London, which is dedicated to the development of low latency and torque control super light robots. And their aim is to provide the robots to researchers so they can concentrate on testing the best of artificial intelligence algorithms in physical robots without having to worry about the hardware. So thank you very much for doing this hard work, Greg and Charles, and welcome to the podcast.
Thank you. Yeah, it's a pleasure to be here.
Indeed.
Okay, and then your company, React Robotics, is about to release or to put into the market directly the DogBot robot. What is a DogBot robot?
Well, DogBot is a quadruped, so it's four-legged robot, and it's really there for people to develop new algorithms for walking. It's quite interesting to have a robot with legs, because then it can go similar places people can go. So that means the terrains can be harder to traverse, harder than, say, wheels or tracks can traverse. One of the sort of main examples of that is stairs. So teaching a robot to climb stairs is sort of one of the goals we have here. And just that will allow it to access the same places that people can go, as we say.
But when you mentioned about the importance of being quadruped, you mean in comparison to wheel robot, you mean that?
Yeah, wheels and tracks, yeah. So there are some limitations. So with legs, you can step over a gap, you can step over an object that's quite large compared to the size of the robot. A wheel, you could get over maximum half the height of the wheel, but with a leg, our legs extend to about 60 centimeters long. So you could get over objects that are less than that, but still very large.
Yeah, and especially also in uneven terrain is very convenient. Also, the legs. Yeah.
Yeah. So trying to balance on uneven terrain is one of the sort of main research challenges, I think. So stabilization is very important. And if the robot can traverse those terrains, that opens up commercial applications in the long term in places like construction sites. Places with difficult terrain where usually only people can go.
Okay, and then so you have this DogBot that is a quadruped, and more or less, just for the people who haven't seen the pictures yet, because we are going to put some pictures on the show notes of the episode, and then for those people, so how can you describe a little bit how it is in size or what it does contains, if it has, I don't know, does it have a head?
No, it's quite sort of symmetrical without a head. I mean, there's a body, and the body is, like, including the sort of end sections which house sensors, is 86 centimeters long. Then at the top of each leg, there are motor casings. So the maximum width is 56 centimeters. And then each linkage of the leg is 30 centimeters. So it's the highest it would be about 60 centimeters. So that gives you a rough idea. But it's quite minimal. I mean, there's not lots of stuff hanging off it. The body is quite small. It really allows for a lot of articulation of the legs. So they can fold around the top or the bottom of the body. So it's pretty pared back really as a design. There's just what's necessary that's been left.
Okay. So I think that people get a little bit an idea, except for the people in America, because you mentioned in centimeters. So what about in feet? So joking.
Centimeters is 1 foot. So the linkage leg is 1 foot, and yeah.
Okay. Yeah, I was just joking. Yeah. That's okay. And the question I wanted to ask you is, why did you decide to build such a robot? Why this one?
Originally, we were our company actually was doing work in artificial intelligence, and we were looking for bodies to an embodiment for our intelligence. So it's very easy to learn from canned data, but learning to interact, we were particularly interested in making our software learn to interact with the world. So the project originally started more as a side project to try some of our algorithms on controlling a robot in the real world.
Okay.
And it sort of everything followed through from there. So, we sort of started talking to other people, and they had similar interests. And that really encouraged us to sort of take it from a side project into a proper product.
One of the challenges with a project we were doing was the self-driving car project, part of a grant we were involved in. And so trying to get real-world data there in areas where there were a lot of pedestrians is we could drive cars and acquire data, but testing that then would have been difficult. I mean, testing your vehicle, your 2 tons of metal in front of real people is a little bit risky. So, but a small robot like this could walk. It only weighs 20 kilos, so it'd be safe for this to walk amongst people, and we could test our algorithms safely then. So that was one of the reasons we went for something small, but could still get around where people go.
Yeah, one of the reasons for the size is make it large enough to interact with a human scale environment. So it could deal with steps, it could deal with pavements, it could deal with obstacles that people would normally deal with.
Okay, but not too big that can create problems to the people when something goes wrong and then crash and hurt them.
Yeah, with safety, it's not going to break a leg if it falls on it, or it's a reasonably safe.
Okay. Okay, and then so based on what you mentioned, I have a question that I don't know if it is here in the list, but I want to jump to this one. It's about the control algorithms. So you are providing this robot that works with ROS, and then we'll talk more about the interface with ROS later. But are you providing to the buyers, are you providing any type of control algorithm that already does some tasks, makes the robot perform some tasks?
At the moment, yeah, we've got some simple gait generation, so you can instruct the robot to go forwards, backwards, turn, move side to side, and it has some basic balancing functionality. But at the moment, the algorithms are fairly minimal. It's something sort of we're concentrating on the moment of making the robot work and be ready for researchers to use. And then once we're satisfied with that, then we'll move on to hopefully provide in the future. We're hoping to provide a much richer set of
control
algorithms.
Makes sense. I was just worried for the people who. So I can see that many researchers are interested in how to generate gaits for quadrupeds or any other type of robot, but some other people maybe is interested on building applications on top of your robot, and they don't care about the gait, but just that the robot moves and goes to the direction. So they do have this basic algorithms that allow them to control to go to one position. I mean,
Yes.
the gate just is a gate. So the direction to which to go, it has to be built by the buyer, by the researcher. It's a
Yeah.
Okay. And then one question here from the pool. What is proprioception?
So that, I guess, that's looking at how the body interacts with the world. So there's a sort of combination of haptics, sort of getting feedback from touching the world, and then also just generally having this just a lot of sensors, or a lot of capability to sense and observe what's happening through the motors and the positions of the joints. I mean, we spent a lot of time talking to researchers and finding out really what they wanted from robots. And a large part of that was to actually have not just the sort of minimal amount of sensors, but the maximum amount. So there's a lot of overlap and redundancy in sensors, and get as much data as possible to get a rich an idea of what's happening. So we output sensor data for the current, which is the obvious one, which is motor torque, essentially. So what we're providing and how the environment is affecting that, and the position, so the angle and the speed. And we've looked as well at other sensors. So something we discovered, which is quite interesting, is the quadrupeds with foot sensors. Typically, those foot sensors don't last very long. So you might have a touch sensor. Yeah, they're getting hit a lot, basically. And there's going to be dirt and dust and impact quite regularly. So things wear out quickly. So we're investigating putting sensors further up the leg, actually putting strain gauges on the carbon fiber of the lower leg, so we can we have essentially a load cell, basically, which is understanding how much the lower leg flexes. So it's minimal amounts, it's not really observable, but for our sensor we can see how much that is, and we can quantify that in terms of force on the leg.
Okay. And so this proprioception is basically about censoring the internal state of the robot. It's basically because it's about the joints, which position, and if it has touched the ground or something. And do you include any external sensor, like a leader for detecting the environment around?
We will provide it, but one of the reasons why we're using ROS is that there are so many tools and SLAM tools and things like that you can use with LiDAR and things like that. And so we're really leaving a lot of that kind of sensors up to the end users about what they want to use and what they want to integrate.
Okay. Okay. So you can any person, then they will have to integrate their own sensors, like a laser or a point cloud, maybe. So it's quite convenient to put a point cloud in the front of the robot to detect.
Yeah, you could fit something like the Intel RealSense in the front compartment. So we have it just blanked off at the moment, but there's space in there to fit something like that, so that it's also protected from impact.
Okay.
We will be providing a sort of standard set of sensors. We will have something integrated if people just want it off the shelf, but it will be a particular sensor with a particular set of ROS algorithms. But that'll be an optional extra.
Okay. And what about in terms of characteristics, in terms of computers and speed of the network? So your robot contains inside a computer, and then there is a network for communicating with the motors and the sensors of the motors. And so can you tell us something about that?
Yeah, so we're for communicating with the motors to get enough bandwidth for the sensing we're talking about, we're using an ether-based technology called EtherCAT, the chipset anyway, so that we can have 100 megabit network that's communicating all the information from the motor controllers, and also with also some other sensors dotted around the robot, including IMUs and the like.
Okay, and which kind of computer do you have inside?
There's a space for a mini ITX. So we have it's a standard form factor for small embedded computers. So so you can basically fit a small standard PC inside. It'll also fit sort of things like the NVIDIA Jetson development board. If people wanted to use one of those, for example, will actually fit in that space, and it follows a similar form factor.
Okay. But that's kind of an option that the buyers can put in there.
Yes.
You mean?
Yes.
Okay. And then communicate this computer with the internal computer of the Is it?
Well, that space is for the internal computer. So that would
okay.
Ethernet platform. So you have to run the platform control software on that computer. But
yeah, and then there's so each motor has its own motor controller, which is it's a small computer basically, with like ARM chip and things like that. So that's something we developed in-house, so that we can specify that for the type of motors that we have and the type of communication we want. So that's an in-house.
Yeah, so and that's the one that is connected through EtherCAT around the whole body of the robot, going to the different controllers. 12, okay. And so you mentioned that it is 100 megabits per second, and it is the EtherCAT. And then why does this robot need such a fast loop speed? I mean, I understand that it's for a fast loop control, but can you explain to the listeners why it is required?
So I mean, if you look at the thing, look at what people are doing. They want maybe for the control it's not necessary, but for actually getting feedback about what's happening, all the torques from the motor, so that you can understand when the foot is actually getting in contact with the ground, for example. So you can understand when you want to stop moving the foot downwards and keep balance. If you look at the literature, the sort of typical rates of about 100 hertz, people have said, is just not fast enough to make these decisions, change the motor direction, and keep a good balance.
Yeah.
So
I see.
So we're targeting update rates of about a kilohertz, and just to get that data back and keep the latencies low, so that you can do some useful things with it once you get it back to the computer. You really do need a fast network. Another thing is the EtherCAT provides is time synchronization between all the controllers, so you can synchronize all the data coming in from the sensors and be sure when each sensing reading was taken, so you can allow for that.
Okay, makes perfect sense. And then the faster it is the network, the more updates one can have from the sensors, and then you can take quicker decisions based on especially for the stability, especially.
And also, I mean, when it's also about deciding when so for example, if you want to decide when the foot is actually planted on the ground, you want to have a look at at how the torque is increasing. You want to look at the patterns. You want to say, like, if you're outside and you're maybe on the surface isn't so stable, you want the torque might start increasing, but it might not. It might be on a leaf or a twig or something, and that might be cracking and going down. So you want really a fairly fine-grained view of what's happening on the foot to decide when that foot is actually planted firmly, and you can rely on it to provide enough force to provide support for the robot. So that's part of the motivation for really getting these high sensor bandwidths back.
Okay, makes perfect sense. And you mentioned that it runs in ROS, but the ROS is something that is running inside the computer of the robot, or it's do we have to have an external computer that has a kind of I don't know, like a node that communicates with the internal computer, and then this external computer is the one that runs ROS and provides in topics. So how does it work?
So at the moment, the intention is that the internal computer will run all that's needed to run the platform.
Okay.
Though, I mean, again, we're delivering this to researchers, so if there's a requirement for more compute than we can get comfortably on that small computer, people can add, networking and Wi-Fi to offload some of that if they're needed. But the intention is that the robot should be self-contained and be able to sort of navigate the world without being tethered or closely knit to any particular network.
Okay, so it's the internal computer that is, you switch it on, and then it's running already ROS. Maybe some other things there about, in a different API for some other systems, I don't know. But ROS is there. That I'm pushing about ROS because this is the ROS developers podcast, and then the people, so, okay. And very important question, which version of ROS is in there?
I think it's melodic, as far as I know. Yeah,
we're using melodic at the moment, and we're using a standard Ubuntu 18 installation with melodic.
Okay.
Though with these high data rates, we are hoping that ROS 2 will come out soon because that addresses a lot of the real time aspects that I think people will want to see when doing this sort of research.
Okay, but then now I'm checking here the questions, and then I remember that you mentioned to me about a Python interface, and it was a kind of a wrapper layer on top of ROS. So it's what is this about? Okay,
so we have a few layers. We have the very lowest level of API doesn't use ROS directly, so we put a ROS interface on top of it.
Okay.
That's mainly because at the very high data rates, if you're wanting to do pattern recognition, the latencies in ROS may cause problems if you're doing things at a kilohertz.
Okay.
And we also have a Python interface which lets you talk to that API level, But then those two are actually used then to make ROS nodes, which then can be used to control the robot.
Okay. So it's like two different types of interfaces. Then the one is the Python one that it's we'll say it's for very, very, very fast applications that require to have very fast access to the sensors and actuators. And then the other one is the ROS that has the limitations that we already know about ROS.
Yeah. So the two low level, the low level code is C++. Then there's the C++ and Python sort of at the similar level, and then the ROS comes above that, where to give people that
Okay, and then you mentioned about the ROS 2 plans to port this. Any work on this already done, or maybe if I know that you are releasing now the so that's for all the listeners. Let me tell you, for all the listeners, that this is the hot news. Let's say, okay, so it's hot news. So React Robotics that is doing this presentation here on the podcast of the product that it's releasing. When it is the actual date of release, the exact date of release?
For the simulation side of it is something you can download now. So you can download everything you need to compile that. The robot, we don't have a fixed date yet. We're kind of working as hard as possible, but in the next couple of months, in the next month or so, we should be demonstrating the robot.
Okay.
And then we'll start taking orders for the robot. So there will be a waiting list and sort of a limited availability initially. We're really keen on getting working with really exciting researchers, and we've already spoken to a lot of researchers who are really interested in getting hold of this. So it's quite exciting for them to have a robot that's been built for doing machine learning research. So there has been a lot of interest in that so far. So yeah, we're really excited to get that out as fast as possible.
Okay.
Yeah.
Yes. Actually, you mentioned about the simulation, and we were collaborating in order to provide also this simulation on the cloud, and then having people that they can already open this project, this simulation in the cloud, and then run it directly, so they don't have to install anything in there by using the ROS Development Studio.
Mm-hmm. Yeah, so people can go to the construct, and I don't know if you've put in that as a example file yet, but obviously I guess that's where it's be headed, and they can download it. Well, not download it, so they don't need to. They can just start using it in a web browser.
I think if we have it trotting around in Gazebo, so it's ready for people to start to play with.
Yes, so we have prepared two things. I'm going to put the links beneath in the notes of the episode. That is, the first thing is that actually you can go to the ROS Development Studio right now and then open a new project, an empty project, whatever. You open and then you decide to launch a DogBot. So you can only click there and then it will spawn a DogBot there with the controllers already there. So you can go. After we finish, you can go and check that. So so the engineers have been working on that. The engineers from our team and from your team. So maybe it wasn't communicated up to the top level already, but that's work that we have published this Monday. So this Monday was released into production. So this Monday, and for the listeners, we are now on Wednesday. So. Okay, so those things. But actually, the thing is that you can go to the ROS Development Studio and spawn a DogBot by doing nothing, just clicking, and then it's going to start working. You can send speeds and move around and so on. And also we have another ROSject. A ROSject is a project that contains a simulation, and it allows you to modify if you want, or to include, for example, a sensor on top of the robot, modify the URDF and so on. And so we have that, and then we'll publish together with this podcast. Okay, so I will put the link here, and of course sending you the links for your reference. This is about the simulation of the robot. And then so here it was a question about that. It is about the simulation that already provides a controller. So also so anybody that spawns this simulation can control the robot into different directions, going to one side or to another.
Mm-hmm.
Yeah,
it's an early version. It's an early version of the Gate software, but it's enough to get you going.
Okay. Yes, and I have seen it and tested myself, and I mean it's working for moving the robot around. So in different scenarios, so it's good enough. So for the people who is not interested on the gates, they can use this perfectly for other applications, like making the robot climb a stair, or
The stair climbing isn't included in what's been released. As I said, it's an early thing. It'll work. It'll walk around on flat surfaces.
Okay.
So if someone's more interested in the perception side of the research, then it means they have a platform that can walk already in the simulation, and they can start investigating a level up from there, which is perception, or beyond that, which is sort of decision making. So they can go up a few levels. Without having to do the low-level walking bit first.
Exactly. That is very interesting, but it depends on the type of researcher, of course.
Yeah.
And and then so let me tell you that we have covered all the questions here. So it was not a straight going question after question, and then I'm checking, okay, what's the next question that remains here for me? But I see, we already discussed that, so even without asking the question. Okay, so just to finish, that your robot is on pre-order.
just to clarify, it's on pre-order now.
Yeah, you can go to our website and register your interest for pre-order, and then we will give you, we will notify you a date. But I think the best thing to do is contact us, talk to us, tell us what you want to do and what your research is about, because we're really interested to hear from people directly, and that always helps to get you ahead of the queue.
Okay, of course, I will put the contact details for you both on the episode show notes. So any of the listeners that want to contact you, they can get those information there.
Yeah, great.
Okay, great. Okay, so thank you very much, Charles and Greg, and I hope you will have a big success with this robot. Of course, we will keep collaborating for putting the simulation and also transferring to the real robot. So whenever you want to do this kind of demonstration, yeah, so that would be super cool, super great. And thank you very much.
Thanks, Ricardo.
Cheers.
Thank you. And for all the listeners, let me remind you that if you want to become a roboticist or an AI researcher that is applying this knowledge to the robotics, then what you need is to learn ROS, because ROS is the standard in robotics. How can you learn ROS fast? How can you do it? Very, very simple. Have a look at the Robot Ignite Academy. We have created at the Robot Ignite Academy the 30-70 teaching method, which is based on 30% of the time learning the theory and 70% of the time practicing with simulated robots. We provide a complete path for beginners, starting by teaching you about Linux for robotics and Python for robotics, in case that you don't know. And then we continue with the basics of ROS, and then at the end, how to build your own ROS robot step by step. Have a look at robotignite.academy. Also a link here on the show notes. And that is all for today. See you next week with a new lesson from the experts. And until then, keep pushing your ROS learning.
The Ross Developers Podcast. The Ross